Also looking for time.
Okay, good morning everyone. Take seats because it's going to be pretty full in here. Get going. Right. So, what a thrill to see everyone here. So, good morning to those in the room. Good afternoon, good morning, good evening to those online, wherever you are in the world. Thanks for joining us for this week. It's a real thrill to see everyone here together. And with no further ado, I'll hand over to Massimo Stiavelli, the head of the JWST Mission Office, who will chair the first session here, and we'll begin the introductions. So,
thank you for joining us for this exciting meeting. I'll start right away. The first speaker is our interim director, Nancy Levinson.
All right, thanks so much, Massimo and Chris. And I'm just so excited to be here this morning. So looking forward to the next few days, where I think we're just going to hear so many amazing results coming out of the work that all of you are doing with JWST. And so this is just a real thrill to be doing this. So beyond the very standard welcome, and it is the warmest welcome for all of you who are here in person and those of you online. I've just been so positively amazed by the strong reaction to this. It's those of you online. I've just been so positively amazed by the strong reaction to this. It's so happy to be doing that. Now to see if I can advance the slides. There we go. I actually want to start by taking us back just 5 months. It's pretty amazing what we've all been doing in 5 months. And so big thanks to our Office of Public Outreach here, who put together a little bit of a reminder.
Take in this moment. Remember this time right now before you see everything. I mean, this is going to change everything.
This is the dawn of a new era. This is the result.
6.5 months ago, a rocket launched from Earth, carrying the world's newest, most powerful deep space telescope on a journey 1 million miles into the cosmos. It's a new window into the history of our universe. And today we're going to get a glimpse of the first light to shine through that window.
Thrilled and I'm relieved because you know when you start something this big, you know there's always a possibility it might not work. It did work. We are so proud.
I think we should all feel extremely fortunate to be here at this moment in time when all of this is happening, in the building where we control this technological marvel from 1 million miles away. The infrared photons that have been traveling across the universe for billions of years are captured by Webb's giant segmented mirror. They nestle their way into some detector, amazing detectors that it has, and then they're sent across that 1 million mile chasm back to us, and then disseminated to the rest of the world.
This is where a new scientific journey begins, as thousands of astronomers throughout the world will now be able to access the JWST data for the first time to start doing science.
Webb's first images are just the first look. We have a fully operational telescope to make new discoveries, and the science will fuel the sense of wonder and exploration for generations to come.
Words of the famous Carl Sagan, somewhere something incredible is waiting to be known. I think those words are becoming reality.
And indeed, they really were only the beginning. The first images and spectra, those were just the raw materials for all of us. And so that's why it's been so wonderful to watch what all of you have been doing with that material over the recent months. That there's more that needs to be added to that into real science, and that is in fact what's happened. So these are much more than beautiful images or just basic spectra, but they're genuinely giving us some insight into the universe. Some of the video showed you some glimpses of what was happening leading up to the release of these early release observations. And it really was just a glimpse, because the whole process was something that occurred over many years, over more than 5 years, to really be able to capture the full breadth of what JWST is capable of, considering the different instruments that we'll be hearing about some more this morning, and also considering the variety of science themes that are accessible. And I think these first results give us a nice broad overview. But actually, the beginning goes back much longer than that, much longer than those 5 years of planning those early release observations. And in fact, we are here in this auditorium in a historic locale. Because this was the first conference to discuss the Next Generation Space Telescope in 1999. And it was a really exciting conference with lots of different things that were discussed to figure out the science and the technology that would be needed to turn into this great capability that we have. And that's one piece that's really important for me, is to think about the focus at the early days on what was the scientific potential that was needed. What were the things that we needed to explore, the questions that we had that we needed to answer, and then to define the capabilities that were required to find answers to those questions. And of course, one of the really exciting things that comes about afterward is that science advances, and there are entirely new fields of study that didn't even exist in a serious way in 1989. For example, the whole study of exoplanets, that's a tremendous capability, and we're looking forward to tremendous advances with JWST, and we'll continue to hear some of that. I personally want to express my gratitude to the people who have been involved in this mission over these many decades. I myself was not part of these very early days, and I know that I'm standing here and able to talk about these wonderful outcomes because of what many of you, either in the audience here or also elsewhere, really made possible. And in fact, we'll get an even better opportunity to celebrate that this evening with a reception that I hope all of you who are here in person will be able to join. Something else I do want to point out, though, from this first workshop is on the right-hand side of that front cover, the image is a simulated galaxy at redshift 1. And you laugh because this is what we see. This is what we've done, going even better. In fact, the lowest redshift image in the postage stamps there is Z of 2.8. So this is just a tremendous resource that we and you have been able to use, and it is just so exciting. So this is but one example. This isn't even the field that I work in, and I'm so excited about it. And as I said, just looking forward to the next few days when we'll be hearing so much end to end in the cosmos to learn about this great capability. So I'll close there.
Are there any questions for Nancy? If not, let's go to the second speaker of the session, Dr. Jane Rigby from Goddard Space Flight Center, who will tell us about the science performance of JWST. That, I don't know. Yeah.
Oh, a clicker too. wrong one. That's the bottom one. One, can you hear me? Two, slides are good? Great. I'm so excited to be here. Oh my gosh, this is my first in-person conference since January 2020. Now it's green. All right, now you can hear me. I'm so excited to be here. Thank you for being here either in person or online. This is so exciting that they asked me to talk about science performance. How well is the observatory working right now? What does a user need to know to write cycle 2 proposals? So we'll do that. And then personally, I am so excited to get to the talks with new science results. We've been waiting for such a long time. No. All right, clicker's not working. Let's do that. All right, so what I'm going to talk about today, I will do one slide of mission status at a very high level. I will then walk you through the spacecraft performance that's relevant for users, the guiding, tracking, and pointing performance that we need to know as users, how the downlink is working, how the telescope is working, because you'll then have subsequent talks by each of the science instrument teams, but I'm going to cover the telescope, and then an overview of the imaging and the spectroscopic sensitivity, and then we'll talk a little bit about lifetime and close. All right, now the clicker's working. All right, so mission status in one slide. As you know, we launched on Christmas a year ago. We're in a nominal orbit around L2, just a phenomenal injection and mid-course corrections to get there. Sunshield and telescope both deployed nominally. Pretty much honestly perfect. Phenomenally is better than nominally. I'll talk about lifetime at the end, but the propellant on board, we have propellant on board for more than 26 years of mission life. Commissioning, that really hectic 6-month period, mostly happening here at the Institute, finished with all 17 science instrument modes approved and ready for science. And of course, those instrument modes have been working for the last 5 months of normal operations. Science and mission requirements have been met or exceeded across the board. Nancy just talked about the release of the first images in July. And so now is the really exciting part where the science papers are starting to roll in. So that's mission status in a slide. This doesn't work. All right. Okay. So just to start by acknowledging that something like 20,000 people worked on JWST at some point, and about 600 people commissioned JWST. So just a note of gratitude for that truly international, worldwide effort, multiple institutions to bring us the beast that we have. And so during commissioning, we met pretty much every day upstairs in the boardroom to walk through what we had gotten in the last day, how things were looking, what worked, what didn't work, what we didn't understand, and what was the emerging science performance. And so it's due to that tremendous work over 6 months that we now have it, we have now characterized the science performance and we can walk through it. Okay, so in one slide, this is science performance, and then we'll walk through it in more than one slide. Almost across the board, the science performance is better than we expected. The point spread function is almost twice as sharp in each of X and Y than the requirements. The pointing is more stable. The point spread function stays the same over time, better than we expected. Pointing and guiding are better than we expected. The throughput, almost across the board, is better than expected. And in yellow here, I have references to the PASP papers that describe that performance in more detail. As designed, which was a level 1 requirement, JWST is limited by the backgrounds from the sky, not its own backgrounds from stray light or thermal emission for all wavelengths less than 12.5 microns. So that's what it was designed to do. There we go. So let's walk through spacecraft performance. It's slewing nominally. It's settling faster than we can acquire the guide star like it's supposed to. Thermal performance is great. We have power to burn. We have power to spare. Fault management has been about what you would expect for a new observatory, a little better. We had 7 safe mode entries during commissioning. We've had 1 during normal operations. That's okay. That's what's supposed to happen. The causes for each of those is understood, and we've either done patches to flight software or adjusted the set limits. So that's all great. Let's now go talk about the telescope. With the acknowledgement that there are people in the room and online that are more experts in the telescope than I am, but let me give you the overview. We're pointing great. We're pointing in general better than 1/10 of an arc second compared to our requirement, which was 1 arc second. That means that for things like the IFU, we can just go straight there without a target acquisition, which is an efficiency gain. We're guiding to about 1 milliarc second. There's a little jitter ball down in the bottom right. 1 arc second, 1 milliarc second, 1 sigma per axis compared to a requirement of 4. So that's about 2 to 3 times better than Hubble points, right? Very stable guiding, which translates into better image quality, right? We just lock on and we stay very stable. And there are issues, we are not seeing issues with, say, fuel slosh or other disturbances of the observatory while we're observing. Tracking moving targets, we had a pre-launch requirement to be able to track anything moving at up to 30 milliarc seconds per second, which is the maximum speed that Mars can go. So that was our pre-launch speed limit. There are scientific reasons to want to track faster than that. You'd like to get near-Earth asteroids and comets as they're closer to the sun, so they're more active. We demonstrated during commissioning and early science observations speeds up to 110 milliarc seconds per second. So that's staying fixed on the science target, and then the guide star is sliding across the guider, right? So that you're not moving sidereally, you're fixed on that moving target. So we can do speeds up to 110. It's not very efficient, but we can do it. And so in cycle 2, we're going to be offering speeds up to 75, but you can specially request higher rates if there's a really compelling reason. Just a demonstration that yes, moving targets, we can track them. And then another example, this is the DART impact. There was a lot of special work here in this building to be able to track the DART, to be able to track the asteroid as the DART mission slammed into it on purpose. That's that speed of 110 milliarc seconds per second. We practiced on another asteroid, and then we were able to successfully execute that. You can see the plumes of debris coming out of that asteroid as it was smacked into. So that was us, that was JWST working to support a planetary science mission. There was a bunch of extra engineering things that we needed to do to support a tracking rate that fast. But we can, so that's great. So our speed limit is now 1.5 times faster than we promised before launch, with higher available for good reason. Downlink, data collected in space are no good if we don't get it to the ground. The capability is 57 gigabits per day to the Deep Space Network. So it's gigabytes. And then we have a mission requirement to download for data for 8 hours out of every 24. We only have 11% margin on that, which is a way of saying that Cycle 1 Science has packed in as much data volume as we can, because we want as much science as we can. To mitigate that really tight margin, we've been requesting more like 12 hours a day contact from DSN. In general, we can skip a contact with no impact. We make it up on the next several contacts. The recorder, if we don't talk to the spacecraft, the recorder will fill in about 24 hours, right? So if the recorder fills because we miss multiple contacts, then JWST will stop science observations and quietly wait for instructions from the ground, right? There have been some impacts to Artemis. Artemis, the moon mission, gets priority over JWST because it's a human mission. So depending on the phase of the moon, we can there can be times if Artemis is going toward the moon when the moon is full, that's the same direction as L2, right? So the DSN pointing toward L2 is those resources are going to Artemis, not us. So in that case, we can lose contacts, and so we did have that impact this summer for some of the planned Artemis launch windows, where we ended up having to, you may have seen your observations rescheduled. We had to reschedule for a bunch of low data rate observations. We anticipate that impact will be for Artemis 2 and 3 as well. It's shared competition for DSN. We had some impacts for when Artemis actually launched. It just splashed down. The lunar phase was not at all full moon, so it was less than we expected. We actually got most of our contact times than we expected, and there wasn't that much impact from the actual launch. But you should expect that that'll be true for Artemis 2 and 3, that there will be some impacts. All right, let's walk through image quality, wavefront sensing and control. Let's talk about micrometeoroids. And I want to highlight the beautiful PASP paper submitted by Mike McElwain and et al. That has a really lovely overview of the telescope design and the performance. Okay, so image quality. The upshot here is that we're diffraction limited at 1.1 microns compared to the requirement of 2. So that's a wavefront error of 80 nanometers is 1.1 microns. Okay, I'm going to switch back and forth between those a couple times, but 80 is a diffraction limit of 1.1 microns. In practice, as we're controlling, so we're sensing every 2 days. This is where that margin comes from. This is a figure by Marshall Perrin. At the left, you can see the little triangles are what the requirements are. Do I get a pointer? Oh, okay, I do. I'm going to actually do this on the screen. So the triangles at the top are what the requirements are, and then the bars are what we actually delivered, right? And so the space between the triangle and the bar is showing where we had margin. And so you can see starting at the right that the instruments are better than we expected. So that's part of why the image performance is better than we expected. That the instruments are delivering a cleaner wavefront than expected. And then we have less image motion than we expected. So that's more margin. The telescope is more stable with time than we expected. So that, again, is some margin. And you can see how this is rolling up to build a telescope that's twice as sharp as we expected. And so you can see that really the only thing where there was almost no margin is this is what is the quality of each image segment, because we measured those on the ground in a cryovac chamber. And so those are very close to what we expected. But then, and we're controlling as well as you can control for the number of actuators that we have. When we tell it to move, it moves the way we tell it to. And so you can see that's where we get rolling it up, the tremendous wavefront performance. This is also a plot from the McElwain et al. PASP paper. On the right here is the wavefront error. Remember that 80 is what we're controlling to. So every time we hit 80, we issue mirror corrections and we make the mirror better. But I want to point out that 150 was the requirement. And I tried to put a bar of 150, but it doesn't fit on the plot. It's up, it's about at the, it's up off the chart, right? So 150 would have met requirements. But this is what we're looking at right now. So you can see as you just look at the mirror stability versus time, that we have a nice state, that our mirror, slowly drifts as we sense it every couple days. And then it gets these tilt events where stress is released probably inside the back plane, and we get a tilt where the mirror moves a bit. And then we correct those down, and we get, again, a nice, beautiful wavefront. And then we get another tilt event. We say, okay, we should fix the tilt. And so that's what we're seeing as we go through. We're seeing in the last, it looks like those tilt events may be getting less frequent with time, as we'll see. But there have been, the last couple weeks have been beautiful, where we just measure every 2 days and we don't have to do anything. And then finally it drifts up toward 80 and we correct it. Right? So we're getting this beautifully stable telescope, which is, we knew the telescope would be dynamic, that it would be, that the mirror would be changing with time. It does, but it's nice and slow, which again translates to better science performance. Micrometeoroids, the joke is that our record was perfect. The whole time the telescope was on the ground, it never got hit once. In space, we get hit at about the rate we expect. We get about 1 micrometeoroid event per month that is big enough to affect the wavefront. Remember that we're wavefront sensing with exquisite accuracy, better than we can correct. So we see even really small hits. So we've had about 1 per month that affects the wavefront, a smaller number that we can, more that we can see on the pupil image, but that don't affect the wavefront. We had 1 hit that was bigger than we expected, that had a larger change to the wavefront than we expected. That hit in late May, and it increased after correction the total wavefront error by 9 nanometers. Right? So it was a significant hit. And you can see it right here. It's the hit to segment C3. And that's after correction. That's just damage to the mirror that we're going to have to live with due to that micrometeoroid impact. And it's not small, right? It's a foot across. So we have spent a lot of time since that hit in May. We formed a micrometeoroid working group working to understand what does that mean? And what, if anything, should we do? And we understand a lot better now the environment of L2, of what as we look in direction, what the population of micrometeoroids is. The thing that is still a bit uncertain is we get rid of the bit, is the connection between the kinetic energy coming in and the damage to the wavefront on the mirror. That's not a straightforward thing to calculate. It's also cold beryllium too, so it's really interesting physics. But the upshot here is we still don't know whether that hit in May was a very rare event that we might get every several years, or is something that we might need to live with about every year. 10 hits of that size would bring us up to 150 nanometers, which is our end-of-life requirement. Okay? So if that is a once a year, once a 6-month thing, then, that would degrade our performance significantly over a 10-year mission. And we have gas for more than 20 years. So therefore, you'll see as you design your cycle 2 proposals that we are restricting the pointing in cycle 2 to have a preference to not point the telescope in the direction of the rain, right? As the telescope is moving through, orbiting the sun, there's a direction of orbital motion for the telescope that is preferentially the direction that the micrometeoroids come in on, right? So if you're observing a sidereal target, your target's observable twice a year, right? I'm going to put the sun right here, and I'm going to be the telescope. As I'm going around the sun, in this direction, I'm pointing into the rain, right? Into my direction of orbital motion, I can observe my target. I also have the freedom to wait 6 months and then observe the same target when I'm going this way, right? So in my wake direction. So we're putting a preference in scheduling to observe targets that are sidereal in the wake direction when the whole telescope is protecting that exposed mirror. So you'll see that. It's called MAZ in APT, the micrometeoroid avoidance zone. You'll see that preference to not point the telescope in the rain if you don't need to. That said, we're still going to support things like moving targets and time-critical observations like exoplanet transits, where that timing is constrained for good scientific reasons. But if it doesn't matter, then we're going to try to schedule you not pointing into the rain, but pointing into the wake direction, and that's to preserve the mirror lifetime. Just to state that we don't have the statistics yet on how often these big hits are going to happen. Okay, I want to talk really briefly about backgrounds, because that is part of science performance as well. We wrote a whole paper about this, so I can be real brief and just direct you to the paper for more. JWST doesn't have a baffle, right? There's no big tube around the front of it. It has internal baffles, but it doesn't have a big tube around the front of it like Hubble does. Therefore, we're subject to light coming in the side that then can bounce off dirt on the primary and get into the optical beam, right? And so cleanliness was a huge obsession throughout all of integration and test. Keep the telescope and all the things that can rain particulates onto the telescope as clean as possible. There's also this huge frill, this Kapton material going all the way around the telescope that protects us from seeing light behind us. It protects light from behind the telescope from getting up into the secondary and into the beam, which is also a big source of stray light. Well, we've measured that on orbit. The black dashed line is our prediction, what we expected to get for total background. And the yellow is what we would get if all the background was just astrophysical. If there was no stray light at all, we'd get the yellow parts. And the data are showing up in general in between those two things. So we're getting less background than we expect, which we're attributing to less stray light than we expect because the mirrors are cleaner and because the baffling worked. All right, and so this is for the 1.2 minutes. This is for a benchmark field that we decided would be a good place to measure stray light. And in general, with both NearCam and NearUs, we're getting less stray light, or less total background than we expected. That wasn't that deep a pointing. We've gone back and gone to 3 deep fields that have public data, including this spot here in the north ecliptic pole, which is one of the darkest parts of the sky. And again, you're seeing that the data are right at or below the predictions. We have less stray light than we expected. So for cycle 2, we're going to drop that assumption a little and assume that the stray light is 80% of our pre-launch assumption. So that means the skies are darker than you expect, so you go deeper faster. For the mid-infrared, in the mid-infrared, the telescope is glowing. right? We're seeing both the glow of the mirrors, and we're also seeing scattered light from the spacecraft and the sun shield. The blue and the red curves here are two different pre-launch predictions. The black is the data from MIRI. And so we're seeing that in general, there's pretty good agreement with our pre-launch predictions, a little bit higher possibly in the, at the shorter wavelengths, but it is still absolutely true. The green here is the zodiacal light. So you can see that as expected, for wavelengths of less than about 12.5 microns, we are limited by the ZODI rather than the telescope itself, which is how it was designed to be. And this is written up in one of the papers submitted to PASP on the backgrounds. Okay, let's switch topics now and talk about imaging sensitivity. So this is it in a table, and then I'll show it as a plot in a minute. But these are such happy numbers, right? The requirement for NIRCam here, the requirements were 11 and almost 14 at 2 and 3.5 microns. That's what's the faintest thing that we can see in nanojenskis in 10,000 seconds at signal noise 10. That's a point source, right? And then the actual is significantly better than that. This is just raw image performance gain due to a number of factors, a better telescope, lower background, more sensitive instrument, and higher throughputs across the board, right? So that's fantastic. The same is true for NIRIS as well. You can see the predictions versus the actual performance. It's just better across the board. I want to take 1 minute and turn that into exposure time. If you are doing background limited imaging, common case, right? Deep field, dark, faint things, then the integration time goes as the square of those sensitivities, right? So you can take that performance gain and say that for NIRCam, deep imaging will be about 2.5, 3, and 3.3 times faster at those two wavelengths than a system that just met the requirements, right? So that gain that's significant gain in integration. Significant gain in integration time, significant speed for surveying, right? Which is a way of saying this is why the data look better than we were expecting, right? It's quantifying that. Okay, and then let's go to, there we go. So this is it, and the way my brain works, this is actual imaging sensitivity. Again, 10,000 seconds, point source, signal to noise 10, right? And I've been making these plots for years, but I got to make them with the real on-orbit performance. Using the post-commissioning version of Pangaea 2, which is what's supporting the call for proposals. It's the engine that runs the ETC, if you don't know what Pangaea is, right? And so just a straight-up comparison of this is NIRIS, NIRCam, and MIRI for imaging compared to our pre-launch prediction, compared to other observatories that we know and love, right? And so, when I first made this plot about 10 years ago, it was okay, how does, what is this new telescope that I've just been hired to work on? How well does it work, and where's the discovery space? And it really is here in this 2 microns regime where we're looking at 2 orders of magnitude gain in sensitivity compared to previous observatories. So that was the promise, and that's what we are realizing. Let's do spectroscopy next. I'm going to first show it in a confusing way and then in a clear way. Okay? All right. Well, first I was going to point out that limiting sensitivity is not the only thing of interest. It also helps that the PSF is way brighter, right? So this is a way of just saying visually that we go much deeper, faster. Well, yes, and also a much tighter, much cleaner PSF helps a lot too. There we go. This is the confusing way, and then I'm going to get clear. The ETC calculates things in terms of, for spectroscopy, in terms of continuum sensitivity. So sensitivity per resolution element in Janskis, right? That's not how my brain thinks. So I've taken this and converted it to limiting flux density. What is the faintest line flux that you can detect in 10,000 seconds at signal to noise 10? All right, so I'm going to go from, there we go. So this is limiting line flux, right? Whereas with ground-based observatories, we're usually up in the 10 to the minus 15, 10 to the minus 16 range. We're going down with near spec in 10,000 seconds, close to 10 to the minus 18. So these again are from Pangaea. So this is what we are getting in on-orbit performance. And so I've got near spec in the MOS mode, near spec in the IFU, NIRIS here in the for wide field GRISM spectroscopy, and again for NIRCam, for GRISM spectroscopy. And then MIRI, there's two ways to plot this. This is the somewhat more conservative way of plotting MIRI MRS performance, right? But so this for me, oh, and then dear Spitzer, dear beloved Spitzer, is up here in purple at the upper right, where just the spectroscopic gains here between what we can do in the ground, what we can do from the ground with 10-meter telescopes, what we've been able to do with Spitzer in space, and then now what is possible. It's just, this is discovery space right here, right? This is why the rest of this conference is going to be really fun and why this is such a fabulous observatory. Okay, I want to talk about lifetime. We have propellant on board to last more than 26 years. That's a public number, so there's a link to where it's quoted. Why is that propellant needed? We needed propellant for several things. We needed it for the mid-course corrections to get to L2. Those worked fabulously, and they were on time, which used less fuel than if we did them late. We also need propellant to dump momentum. It's actually the momentum of photons from the sun hitting the sun shield that we have to dump that momentum. It spins up the reaction wheels, and periodically we have to slow the reaction wheels down by firing thrusters in the other direction. We also need to use propellant to keep station around L2. It's not a stable point in the solar system. If it was stable, then more micrometeoroids would get there. So we're glad it's not stable. But we have to spend energy to stay in orbit around L2. So those are the three things we need propellant for. We never need to do another mid-course correction, so we're down to 2. So before launch, the requirement was that we have a 10-year science lifetime so that we have propellant in the tanks for 10.5 years. In fact, we are looking at 26 years of propellant life remaining. And I can talk more about that if you want to know where that came from. Why do we have more than we expected? It's a number of things. One, December 25th, 2021 was a fantastic day to launch in terms of orbital mechanics. It needed less energy to get to L2 compared to other days in the year. That was just, we got lucky. It was a good day. We had on-time mid-course corrections. The longer you wait to do the mid-course correction, the more fuel it needs. It's less optimal. And we did all of our ranging with our 3 ground stations on time and fired our mid-course correction on time. And all the mid-course corrections were on time and were perfect. And we also, of course, got a fantastic launch. We got a half a sigma correct launch from the Ariane 5. And I actually didn't know that you can program in delta V and the velocity of the launch vehicle and get it right to its part in 10 to the 4. And that still kind of blows my mind. But that's what the rocket delivered, right? We got exactly what we asked of the rocket, whereas we had budgeted spending a fair amount of propellant to correct that in the mid-course corrections, right? And really the mid-course corrections were instead just doing the conservatism of not overshooting. Okay, so we have propellant for 26 years. Propellant is not the only thing that determines mission lifetime. It just is what determined what we knew would limit the lifetime before launch. So what does now? Well, we don't actually know, but let me walk you through what the things that could be. The observatory has all the redundancy that it had at launch. We've had no degradation of the spacecraft. We're still fully redundant, A side, B side, all of our boxes, right? So we have our full redundancy there. Any mission, as it goes on, you can lose redundancy, but we haven't had any of that yet. We've talked about micrometeoroids. We know that micrometeoroids are a fact of life and that they will gradually degrade the wavefront. And we're collecting data. We wavefront sense every 2 days. We do the pupil image several times a year. We're gradually collecting data on what those hit rates are and how it affects the mirrors. And we are going to reduce the time we spend looking into the rain of micrometeoroids starting in cycle 2. I want to just point out that cryogenic mechanisms are not easy, trouble-free things on any telescope anywhere in space or on the ground. Cryogenic mechanisms are operating at low temperatures, materials are more brittle, and frictions are higher. The anomaly with MRS, with the spectroscopy mode of MIRI, where we're seeing higher frictions than we expected, and in fact higher friction than we've seen in ground test. That is a reality that we now are mitigating. We are very carefully monitoring it. We're changing how we rotate that mechanism to try to even out the bearings. But it's a cautionary tale that there's a lot of moving parts in the science instruments, and they're cold moving parts. So I think that's something where we're just going to have to see. But I just want you to know that it's not like, just remember that there's a lot of moving parts within the observatory. And that's, from experience with previous missions, we know that the boxes on the spacecraft and the science instruments don't last forever. So that's a little bit of way of saying that we don't actually know what what's going to limit the lifetime of the mission. But we certainly know that it's not, propellant, we're fine on propellant. And so we are looking ahead to a long and productive science lifetime with this observatory. I want to say that I want to advertise the PASP, the Publications of the Astronomical Society of the Pacific. There is a special issue of JWST that papers have been submitted to that are an overview of the whole observatory, the mission, the whole enchilada. And so I just wanted to list those. We have papers, an overview paper, this beautiful paper on the telescope, paper by our chief missions engineer on the design and the spacecraft. We have a paper on the science performance, which is much of what the slides I just talked about come from that paper. Paper on the backgrounds, and then we have papers on each of the 4 science instruments. So I want to highlight those and encourage you to cite those, because it's a way to cite the people that built these instruments that we're now getting to turn loose on the universe. So I want to close by saying something you all know, that JWST is the most powerful infrared telescope that's ever been built, that it is better than expected. I think there are ways that we can improve the efficiency and that we can tweak things to get better performance out of it. We certainly haven't stopped. And I want to take a moment at the end of my talk to just thank the several thousand people that built this beast and the 600 people that commissioned this beast. It was a lot of time away from family. It was a lot of late nights, and just to see it and appreciate it. It's why we have the science performance and the characterization of that science performance that we do. People really poured their hearts and minds and years of their lives into this thing. So I am so excited to attend the rest of this conference and take a lot of notes and see what people are discovering. So let's bring it on. Thank you.
Thank you, Jane, for the great talk. We have a few minutes for questions. And we'll start with the room and then go online. Any questions in the room?
Let's get a mic so you can hear it online. Hi, Bill.
Jane, great talk. I just wanted to add to your list of thanks the people that are now operating the telescope.
Yes. Yes, yes, exactly. Thank you. So thank you, Bill, for, yes, the people who every day are operating the telescope, sending the commands up to it, calculating the schedule for the next week and optimizing it for the mission that's happening all the time while you're sleeping and while we're awake.
Hi, this is Chris Wanchek. So can you explain the reason why the Artemis slightly interferes with the mission?
Oh, sure.
Again?
So let me back up and talk a little bit about Artemis and why there is a competition for resources. The Deep Space Network, which is what we use to communicate with JWST, is also heavily used by a bunch of missions. I think last time we counted, it was well over a dozen missions. There are times when a lot of missions are asking for DSN time at the same time. When there are, especially like when missions are plunging into Mars, right, when there are planetary encounters. We have for JWST, we want to talk to DSN twice a day for 4 hours a day, 4 hours per contact, so 8 hours total. But we're pretty flexible about when. We just want to empty our solid state recorder and move on. For Artemis is a human mission. Human spaceflight takes precedence over robotic missions in the DSN's priority level. There are 3 DSN stations around the world, so there's continuous contact. For Artemis, which is a moon mission, JWST is always in orbit around L2, so we're always in the direction of the full moon, right? Okay, do a little, all right, make your sun, all right, good. Right, everybody, Astro 101, okay, fine, good. All right, depending on when Artemis launches, if Artemis launches when the moon is new, we don't really care because Artemis is in the JWST direction, right? So one ground station is talking to them, and then we can use either of the other two ground stations. But if Artemis is heading to the moon when the moon is full, that's the same direction as L2, and they get priority over us. So the ground station that can see us is also the ground station that can see Artemis, and they get priority. So given that, there can be periods of up to 3 days where we don't have contact. And the problem is we fill the recorder in a day. So that's just the thing that we're working on, and I want the community to know about. One thing we're requesting in cycle 2 is some low data rate programs that we can use as fillers. The survey mode, the survey category asked for low data rate programs. And what we can do to some extent is fill in those low data rate programs to cover that gap. And we did that this summer when we thought Artemis was launching at what would be the full moon. We ended up executing a bunch of calibration observations early because they had low data rate. But that's why.
Was there a question? Oh, there.
Yeah, and then we'll do it online.
Thanks, Jane. This is all amazingly good news. You mentioned the mirror was cleaner than expected. Is there data yet on how the mirror reflectivity might degrade with time?
Oh, how it might degrade over time is the question. So yes, the mirrors are cleaner than expected due to both conscientious, I'm not allowed to use the word ruthless, to conscientious contamination control throughout the whole integration and test, which is really key because we spent longer in the clean room than we were supposed to, and so that's more time for stuff to build up. We also cleaned the mirrors by hand with a brush. The primary mirror got cleaned, and that kind of reset our contamination budget, and the secondary as well. So that also is part of why the mirrors are cleaner. The main thing that the mirror cleanliness matters for is not reflectivity, but stray light, right? Because it lets particles scatter light from sideways into the beam. We have the reflectivity is quite a bit better than spec. And for degradation, and so that's in Mike's paper, and I'm trying to remember the number off the top of my head, but it's quite a bit better than spec, right? As far as degradation versus time, you can see little hits in the pupil imaging, the selfie, little hits from micrometeoroids, but it's a tiny, like these are really small. They change the wavefront more than they take any gold off the mirrors. So far we haven't seen any degradation, and we're not really expecting that that's going to change significantly over the lifetime of the mission.
Okay, I think our time is up. Let's thank Jane again. Next speaker is Dr. Mario Gennaro, who will tell us about NIRCam status, operations, and performance.
Quick sound check. Yeah, works. All right. Okay. Good morning, everybody. I would say it's a pleasure to be talking at this conference in front of so many people, see this auditorium filled to celebrate the first results from James Webb, and I'm honored to be giving you an overview of NIRCam status and general performance based on our results from commissioning. And it is an honor to be representing this excellent team of individuals, the NIRCam commissioning team, with our PI, Marsha Ricci, and people from the instrument development team, as well as people here from Space Telescope Science Institute, supporting the commissioning and early operations of NIRCam on Webb. As probably most of you know, NIRCam is the near-infrared camera for Webb. It has 2 channels, short and long wavelength, 10 detectors, a suite of filters. We have Grisms for spectroscopy. And as Jane alluded to, we are Nyquist sampled, designed to be Nyquist sampled at 2 and 4 microns with a pixel scale of 31 milliarc seconds in the short wavelength channel, and double that in the long wavelength. So this is your best PSF sampling you can have on Webb. And we have coronagraphic capability on both the short and long wavelength channels. Besides being a fantastic science instrument, NIRCam is the workhorse for wavefront sensing on web. And we do that thanks to special dedicated hardware on our short wavelength channel. Because we were supposed to be the wavefront sensor, we got to be fully redundant as well as so many other critical components on web. And this brings you twice as much the field of view that you would have had otherwise. So our two modules are fully redundant and are separated on the sky by about 40 arc seconds. I will give a brief overview also of the early commissioning days. This is to celebrate mostly the efforts of the Wavefront team who didn't get to speak in this conference. So I wanted to highlight what they've done in the first few months. So this is the first image that was taken with web on the sky. Not the first photons we saw. We did some internal imaging, but this image has a lot of problems. Let's just say that. So we were pointing that cluster, and we may have hit that cluster with one of the mirrors. We don't know for sure. But basically, this was a functional check. And you all know that this is where we got. So fantastic image quality all over the board. And I wanted to give you a brief story of how we got there. On the left here, you see it's a mosaic where each star-like image is actually the image produced by one of the 18 segments of the primary mirror. The first thing that the Wavefront team had to do was to identify those images and their corresponding mirror by moving each segment, in a tilt motion. Once you ID the mirrors, you can bring them in the configuration on the right, where you have mirror to image, let's say, geographical correspondence. However, as you can see, each mirror was producing a quite messy image. At that stage, the Wavefront team corrected piston and curvature of the individual mirror to bring us in the square image on the lower left of the series of 3. And at that point, the 18 PSFs were stacked together. So at that point, we had a fantastic 1.8 mirror telescope in space with a collecting area of 18 times that. So from then on, we used some NIRCam superpowers to further improve our image quality. The first thing that was done was to use this dispersed Hartmann sensor technology, where you have individual grisms, let's say, that straddle pairs of mirrors. So from each pair, you get a spectrum. And as I try to zoom in here, maybe the image quality is not great, but from each pair of mirrors, you get an interference pattern, basically. And the shape of those barber pole stripes tells you how many lambdas of piston there is between your two mirrors. And by having a redundant set, you can match all the mirrors together to get at a coarse-phased state. After you coarse-phase the telescope, then you use another NIRCam superpower, the weak lenses, which are elements in the pupil wheel that defocus the PSF by multiples of 4 wave numbers. So you can combine them to go from -12 to +12 defocus, and by sweeping through that series of defocus values, you get a sense of how wrong your wavefront is, and you apply correction. So the Wavefront team iteratively went between the DHS and the lenses to get us to this point where the telescope was fully phased at about 76 days after launch. This is true for NIRCam only, though. From that moment on, the team had to make sure that the full focal plane, let's say, worked as expected for all 4 science instruments. And so some adjustments were made to make sure that not just NIRCam, but all the instruments were perfect. Another important role NIRCam played in early commissioning was to test for contamination. We've just heard a lot about that. But one of the concerns was that the telescope being sitting very close to Baltimore for so long, there was going to be a lot of humidity in it, right? So, and then we sent it to California, dry and warm, but then again back to the jungle. So water contamination was, let's say, a concern, and the formation of ice was expected to happen on the optical surfaces. So NIRCam, with this long wavelength GRISM, could test for the presence of ice. And from the very beginning, in very hard initial observations, where we used the unphased telescope, it was really tricky, we had immediate, let's say, we understood immediately that basically there is no detectable ice and other volatiles on the mirrors. What you see here in green is the pre-flight prediction from the ETC, but then you see how our, GRISM measurements are like nicely and smooth there without any absorption features there. So there's no water ice, more water ice for you exoplanet folks to look for in your, protoplanetary disks, I guess. Okay, so I'll switch now to more sciencey stuff for about NIRCam operations and performance. I'll start with reminding you that NIRCam has 5 operation modes or APT templates. We have imaging, 29 filters with band passes going from 1 to 100% of the full range. We have subarrays to support bright source imaging. We have wide field slitless spectroscopy with 2 orthogonally oriented dispersion directions that allow for spectral deblending and to lower contamination and confusion. We have time series imaging and spectroscopy, which are both high cadence modes where you can either use the imaging on both channels or do spectroscopy on the long wavelength channel and use the weak lenses for imaging on the short. And both these modes target acquisition for exquisite repeatability, right? You're interested in going always on the same pixels, so your flat field uncertainty goes down, and that's what we do. And finally, we have coronography with 5 occulting masks, and also coronography uses, or must use actually, target acquisition to place the stars or your objects behind the occulters. And probably you saw that in the call for proposal, but from cycle 2, we will be offering coronography simultaneously on the short and long wavelength channel. Right now, we only do 1 channel at a time. And because I needed a 6th item, because of this hexagon thingy, I just wanted to remind you that NIRCam is also can be used in coordinated and pure parallel mode. In particular, imaging can be used in both, and wide field slitless spectroscopy only in coordinated parallels. So performance, we just heard most of it, but the bottom line is the NIRCam and Web exceed all performance requirements for all science modes. In terms of cycle 1 calibration updates, obviously refinements to our data calibration are ongoing. Improvements are expected in all areas, including our darks, our flats, linearity, persistence, flux calibration. High redshift folks know what I'm talking about. And astrometry, both distortion and alignment. All of this is post-processing, is software, is calibration. Our hardware is doing fantastic, and we can go back and recalibrate the data. Things will improve asymptotically. You know that Hubble is still doing calibration in cycle 31. So, we'll get there and improve our performance in those terms. I'll give some highlights on each mode. In imaging, we are better than expected all over the board. In particular, our throughput is higher. Our image quality is in spec, if not better in terms of, for example, of encircled energy. Distortion calibration is very good. We have residuals of the order of 1/10 of a pixel. When you bin those together, the error goes down, meaning that the systematics there's not a lot of systematics, it's mostly random. However, in some detectors, on some of the 10 chips, we are bound to get better as we get more calibration data. In GRISM, our sensitivity is equally excellent, and this plot is to show you that between the row and column orientation, we have very good consistency. And as expected, Module A is better than Module B, because our GRISM on Module A is entire reflection coded on both sides, and so that gives you a better background, basically. And here I highlight just around the water absorption feature what's going on. It's just another view of what I already showed. And this is to say this slide is just highlights one of the first JWST science results that our commissioning team produced. And this actually was a serendipitous discovery in a very short calibration exposure of a super high signal-to-noise line emitter at H-alpha emitter at redshift 4.4. This is just to say that high redshift now, you can claim high redshift only above, redshift 10, basically. For time series, we did some tests of our noise performance, and I wanted to highlight the following. When we do spectroscopy time series, we take spectra on the long wavelength and images with the lenses in the short wavelength. The short wavelength is quite important to monitor telescope drifts of any sort, including, jitter. And Massimo, do I have one more minute? Okay. Yeah. So another fact here is that we were expecting to have some settling times in a time series observation. A settling time is the time you take basically to fill impurities in your lattice, in your semiconductor lattice. That is basically some electrons that are produced, they get trapped there. So you need some time to get to a steady state where you can measure a continuum for your planet transits, where the continuum is stable. The settling time for long wavelength channel is nearly instantaneous, and for the short wavelength is about 11 minutes, which means that padding time series observations to allow for settling is now less restrictive than we thought in the beginning, which increases observatory efficiency. And finally, last but not least, what became my favorite mode, because we worked so hard on this, although I don't understand anything about it. But it's so rewarding to see this plot that I'll try to explain. So on the right, you see the final post-processed image of a white dwarf companion to a bright star at 0.5 arc seconds from this K = 9 star. Correct me if I'm wrong. Do I get 9? Yes. Okay. So yeah, and all you see on the left is our readiness criterion, which was contrast 10 to the -4 at 1 arc second. Well, we reached the same contrast at half of that separation, half of that working angle. And in fact, we reached that contrast if we just take 1 dithered exposure in a set. When you do the fancy things that people do with coronagraphy, stack things together, rotate, change angles, have a diversity basically in your PSF, you can go all the way down to more than an order of magnitude, which is remarkable. So that's one of the reasons why we will be offering coronagraphy in both channels, because we really want to exploit this mode as much as we can. And so I'll conclude by saying all NIRCam modes exceed requirements. All measures are met and exceeded. Cycle 1 calibration will further improve the quality of the calibrated data, but at this point it's up to you, to have fun with NIRCam. And I know some of you already are doing that, so good luck with that.
There is time for some questions. Start with the room.
Thanks for the great talk. I suppose with the better PSF, we're no longer Nyquist sampled at 2 microns. Is there stuff that has impact for, or?
Well,
you might want to.
Our diffraction limit is, the size of the PSF is the same. It's just that we get diffraction limited performance also below the requirement. So at 2 micron, your size is still 2 pixels. So you have let's say higher strain than expected at lower wavelength. But I see it probably Marshall or somebody. I don't know if I said that right, but that's the idea. So. Let's say for astrometry, things like that, you can now probably go a little, bluer and still do good and do better if you have enough oversampling, dithering and so on. You're not plateauing at that PSF size.
Hi, do you think that you will be able to calibrate also data of just group 0 at some point? So when you take data, I mean, we use the UNCAL images.
Yes.
And also sometimes we just like to use only group 0. And so
frame 0.
Yeah, frame 0.
Okay, yes, I can give you something about that. Maybe then Carl probably. I don't know if you're talking about it, but frame 0. When you, if just a summary, frame 0 is our first read out frame, which we save even when we are averaging together multiple frames in a single group. So we save that to give the best possible dynamic range, and typically that would mean 10 seconds in a near-cam exposure with full frame. So that frame is saved. I know that there is some work in progress to include it directly into the pipeline products, meaning that you will be the pipeline will be using frame 0 for pixels that are saturated in the first averaged group. So we're going to do that. There is a possibility of doing even further and actually always including frame 0 as an extra data point, but because there is correlated noise and things like that with the first group, that becomes a little more challenging in terms of implementation. But and maybe, I don't know, do you know when this is going to go live? I mean, frame 0 can be used if you run the pipeline locally. That's for sure.
Yeah, but the calibration is a problem, I think.
Well, so we have uncertainty in our bias, if that's what you mean. Okay, so sorry, I misunderstood. So because it's frame 0, you have to obtain a ramp, let's say a current, you want to have to subtract the bias. Our bias drifts is not yet super well characterized. However, I must say, if you're using frame 0, you're using it for sources that saturate. So you have, very high signal to noise to begin with. There will be some systematics that is coming from the super bias. But because you're only using it for bright sources, that would be, let's say, a 1%, I think, level that you should be good. But I don't have more quantitative measurements.
Yeah, you also use it for moons that move around, and so in order to actually see the moons on your images, you often have to go back to the UNCAL images and use indeed one group or whatever. So there is a lot of problems that we are running into. And I just wanted to make sure that at some point that will be calibrated.
Yes. I figure, no, I mean, at some point I can say yes.
Later.
Hey, Mario. Thanks for the nice talk, and congratulations for your team, because it's quite a lot of work. I was glad to hear that there's still work to go with flux and astrometric calibration. And I'm just wondering when for example, the relative astrometric calibration of even the fields, when do you expect to have that
Okay, yeah, so relative astrometry in terms of global alignment between the short and long wavelength channel and within the short wavelength detectors has been a harder, let's say, nut to crack than we thought, because that we have to. So there are the calibration, cycle 1 calibration data of the astrometric field in the LMC are in most filters, I think. And so we're working on it. I would expect that on a time scale of several months, we might have updates on that. Luckily, the distortions work very well already, so you can still align your individual images to external catalogs, and at that point, you are back to where we would be with a full calibration. But the automatic global alignment steps is going to take a few months, I think, at least, to be fully available. So distortions will asymptotically improve instead, but we're already, as I said, probably a few millisecond RMS.
Thank you.
Okay, let's thank Mario again.
Yeah, and I'll be around if you really have specific questions, and there are NIRCam folks around. I guess we can address those.
I have to apologize to the next speaker because we managed to misspell her last name, but the next speaker is Dr. Macarena Garcia Marin, who will talk about MIRI status, operations, and performance.
Good morning, everyone. How is the sound? Okay? Okay, great. So as everybody, I'm really happy to see so many people attending this talk and sharing the great science and performance of the web instruments. And today I'm going to talk about MIRI. And I wanted to start with, this is the web field of view, and in the top right corner you can see MIRI. So we have the MIRI imaging module that offers imaging, coronography, and low-resolution spectroscopy. And to the upper right, you have these little orange boxes. That's our MIRI MRS, or medium-resolution spectrometer. And I wanted to go straight to a very quick update status of the MIRI MRS. The gist of it is that the MRS is successfully back online. We are performing science, have been taking data for weeks, and things are going well. As many of you know, in August, we did have to pause MRS observations, and this was Jane mentioned it before. It was due to, we saw an increased friction in one of the grating wheels of the MRS, so we had to pause. And the reason for pausing was really we needed to understand the root cause and the final path forward to, operate the instrument in a healthy and to ensure the longevity. So we know the root cause is an increased contact forces in the wheel subcomponents that happened probably during the cool down. And what we're changing is essentially we're going to alternate the direction of the wheel rotation. We'll do some rotations in clockwise and other rotations counterclockwise to actually balance out all these effects and ensure the MRS will be with us for the duration of the mission. The MRS is offered for cycle 2 with no restrictions. The only thing you will notice in APT in an upcoming version is going to be a little clickable box where you can actually revert the order of the grating wheels. You don't have to worry about that. That will be managed internally by our operation and scheduling team. And essentially, you can keep submitting your proposals with the usual short, medium, long order, and we'll take care of the final order internally. Another very quick MIRI take-home messages. These are the things I would like everybody to remember. Overall, the MIRI performance is really excellent and is exceeding our expectations. All modes are offered in cycle 2. And we are seeing unsurpassed sensitivity and resolution, both spatially and spectrally, in the mid-infrared. We are offering high-quality pipeline data products. Of course, there is room for improvement, but at this point of the mission, it's really excellent quality. Our early cycle 1 calibrations are steadily improving. As Mario was saying, it's a matter of collecting more data and making things better. And everything I'm going to talk about here, I'm going to go mode by mode and give some operational updates, recommendations for cycle 2, performance. All that is in JWST or published papers. Feel free to ask questions. If you have any additional questions, please send a ticket to the help desk, and the MIRI team will promptly answer back. So this here, talking about sensitivities, Jane gave a great overview, so I will be very brief. To the left, this is the quote-unquote historical plot she probably did X years ago, where you see the performance requirements of the web instruments compared to other observatories. And to the right, you do have all MIRI modes. The black dots are the MIRI imaging, and as Jay mentioned before, they are actually much better than expected. So things are looking really, really good. In terms of the spatial resolution, you don't have to say anything about this, right? Of course, the previous infrared observatories were trailblazers, and that's kudos to them, but the gains in sensitivity, depth, and resolution, they speak for themselves. So let's start talking about MIRI modes, and we start with imaging. That's our MIRI imager, and we offer 9 filters from 5.6 to 25.5 microns, and this is our full array. It's about 113 by 75 arc seconds, and if you see on the top left, we have our LEO chronographic region. That when we are doing imaging, is a perfectly good portion of the sky to do imaging. So we are including that in all our mosaics, either combinations, etc. So that's good data. You can use it. If you just happen to have a very bright source that is hitting the limit, the brightness limit, and it really saturates since group 1, then you can, of course, go and use our subarrays. Depending on your source and the size you want to do, you may choose a bigger or smaller subarray. And our only recommendation is that please only use subarrays if you need to do, bright sources. It's not just to take a small picture of the sky. It's really for bright sources, and that's their uses. But they're actually very useful when there are like very high backgrounds or very, very bright targets. When it comes to performance, you know that the MIRI PSF is essentially Nyquist sampled essentially for all the wave, a little undersampled at 5.6 microns, but nothing that you cannot fix with a simple dither pattern. Here you have all the PSFs as measured during commissioning, and for 5.6 and 7.7, you see that sort of cross that is going across the center of the PSF. That's a MIRI cruciform pattern, and it is a scattering effect in the detector. We see it in all MIRI modes, and it's just there because it's a detector characteristic. The measure full width and maximum and circle energies, they are within, as predicted, actually, they are better than predicted. And when it comes to photometric calibration, right now in the pipeline, we do have the commissioning-based photometric calibration where we used 2 different calibrators in full array mode and derive our calibration factors. We do have good photometric stability as measured in commissioning, within 5%, and we are getting steadily more and more data, and these calibrations will improve. And right now, we're also focusing on cross-calibrating full array and sub-array, so you have everything in a consistent manner. Recommendations for observers. Basically, for imaging, we're focusing on dithers and backgrounds. To the right, on top, you have what we're calling cosmic ray showers. These are particles that hit the detector, and they can be quite lengthy. It's not 1 or 2 pixels, they are long. So to mitigate that, and also to mitigate persistence, we're recommending long dithers. For instance, in full array, you can go with a cycling large. It works very well, and it really helps diminishing the impact of these features we are seeing. Backgrounds are also highly recommended. As Jane showed before, after 12, 15 microns, you really see all the observatory different components kicking in the background. So it's really useful in many cases to have a background observation to subtract that. Often you can also build a background with your own science data. Like the example here to the left, you have the SMAX field where the sources are smaller than the length of your dither pattern. So that was used to actually create a background, and the correction is shown to the right. So you see that all that stripiness in the detector, some residual flat fields, all that was removed thanks to that background correction. So if your source is filling the full array, consider a background. It is useful not only for many reasons. Moving into chronography, we have 2 flavors. We have a Leo mask and 3 4-quadrant phase masks. And here you have the different wavelengths that they are used. During commissioning, we noticed that there was a straight light from the telescope that found a path, and it's actually creating a glow in the transition regions of the coronagraphs. And this is because there is like a physical mask in there, and it's capturing that emission and sort of glowing. And you see it very clearly in this horizontal edge brightening. So the impact of this is that it made it harder to actually locate the center of the coronagraphs, but also has to be subtracted because you don't want to have that excess brightness where your planet or companion can be situated. So right now we are observers are required to take a background to actually remove this excess emission. Despite of that, for every MIRI filter, the contrast exceeds expectations and exceeds predictions. So you see in these plots, the colorful, the pink and green plots, they are as measured contrast compared with the gray ones. And you see that for all the separations, we are actually performing better. And in the bottom image, you can see after removing the background and really processing the image, the star is essentially disappeared, and the companion is clearly showing. And the authors have been able to characterize all their properties. So things are looking good in coronagraphy as well. I do agree it's a very powerful mode. Operations and best practices. So target acquisition is mandatory for coronagraphy, and currently it's done only in quadrant 1 with a neutral density filter, quadrant 4 with a 15 micron filter. And this is because we're still characterizing the impact of these glow sticks. Back observations are required. And it is really important to remember that the whole processing and PSF subtraction is heavily affected by these glow sticks. And we do have already good guidelines in some papers and recommendations in JWST to actually deal with this. And while we update the pipeline processing, please go to these references and follow the advice that is in there. The astrometric precision at the position of the star is about, we're getting there with an accuracy of 5 to 10 milliards seconds, which is very good. You can also use the WCS information to actually perform relative astrometry at the level 2B data. And finally, if you encounter a situation where the PSF is just, the subtraction is just not working, it is really worth to go to WebPSF and check your optical path difference map relevant to your observations. And I put here like how to do that, because that can actually, if there has been any change in the mirror configuration, it will be considered, and then you will get an improvement in your PSF subtraction. So this is for imaging. Let's move into spectroscopy, starting with the MIRI LRS, the last mode of the imager module. With the MIRI LRS, we offer spectroscopy from between 5 and 40 microns. And there are two modes, a slitless, which is designed for time series observations, and it's on the top left. It's actually a subarray. And a slit that's done in full array mode. We have a smaller slit, you can see it in here, place the source, and disperse the spectra. And this is how it looks like. So this is our LRS slit typical image. This sort of dagger-like source, that's the source in the slit, dispersed, and the dagger shape is actually the manifestation of the cruciform pattern with LRS spectroscopy, and you also see some airy rings in there. Interesting to notice is that, of course, all the targets in the imager field, they are also dispersed, and this is a flavor of wide field slitless LRS spectroscopy for MIRI. And you see all those sources there. This is something that, at this point, the pipeline is not supporting, it's not ready. I mean, we don't have a branch to actually deal with that, but there is a lot of potential in this mode, and we're looking into future usage. But the reality is that you will get the data, so feel free to play with it and share with us what you find. Yes. Flux and wavelength calibration, everything is looking well and as expected. Our TSO light curve, we did time series observations during commissioning, and actually we chose quite a boring target to demonstrate that it was working. And this is the result. It is working, it's unexcited as intended. It's also working very well. Uncertainties are less than 100 parts per million, and these are two different methods that are really consistent across them. The only place where it's a bit not quite that good is at 11 microns, because we did have a much fainter signal in there. Recommendations for LRS, target acquisition is recommended. Be careful with your coordinates. Verification image is recommended, and they are both mandatory for time series observations. For a slitless, we are recommending backgrounds, and you have all the information in JWST. Last but not least, the MIRI MRS, 4 IFUs nested within each other to observe between 5 and 28 microns. We do have very good absolute flux calibration. It's based right now, presently only on commissioning data, and we're seeing some artifacts long wavelength of 20 microns, but still it's looking good, and we are working on that. When it comes to the wavelength solution, it is generally good to about 10, 20 kilometers per second, except in some slices where it's about 50. But overall, there is a lot of work ongoing to improve it, and it's actually performing really well. Finally, the MRS updates on recommendations. Please do dither for your science, do a 4-point dither. You see here, the difference between no dither in 2 points and 4, it's really significant. Dedicated backgrounds, for the most part, we are recommending to take them. You have more details in JWST, but essentially, unless it's it's a point source, just take a background. It really does help. Target acquisition depends on your science. You have to consider the accuracy of the pointing and your science case. Simultaneous imaging, why not? You get extra data, improves your astrometry, and it comes, quote unquote, for free. And also run the residual fringe step correction from the pipeline. And this is a show of a slide. We did this in commissioning, and this is a beautiful composition of MIRI imaging of the Cat's-Eye Nebula and 2 lines observed with the MRS. And it really shows the potential of combining 2 different MIRI modes. And finally, my favorite picture from commissioning, which is the meeting picture. This is the commissioning team that made, all this work possible. There are people in the room, there are people in the building, and everybody, people overseas, of course, and literally everybody's looking forward to seeing the great science results you show here this week. So thank you.
As usual, we have time for questions.
Please state your name and your institution. Brittany Miles, University of Arizona. I was curious about the residual fringing and what you've seen for targets with like obvious molecular features, not like A stars that are pretty flat, or like how's that been going with the team and stuff?
Actually, I'm gonna direct that question to Polychronis, who's up there and is one of our MRS experts, and I think he can actually answer that a lot better than I can do. Thank you.
Hi everyone. Hi Brittany. So the short answer is we're still working on understanding what the impact of the residual fringing is. So we're basically fitting these fringe patterns with a series of sinusoids. You can imagine you could overfit and get some of your science signal away and remove it. So for very faint objects, we see fringing has a less of an impact. So we're still debating on how, if we should actually apply this empirical correction. And there's a paper on archive since a few days that goes into it. It's Gassman et al. And you can see very beautifully how the residual fringe correction can actually capture some of, for example, carbon monoxide features in some dwarf stars. So I would urge to look at that, and we are still looking at where the critical the correction actually helps.
It's still in progress pretty much, but yeah, there's a lot of effort going into that.
Yep, here.
Hi, Margaret Meixner from Sophia. Congratulations to the Miri team. It's super exciting to see all the results. I was curious to know when you think the flex calibration for the imager will be, I don't know, at a level that you're happy with.
That's going to take a while, but yes, we are working towards hopefully updating it in the next month, at least having a look to, when we compare our measurements calibrated from the background with Jane's expectations, they are quite well aligned, but still we are not happy. We really want to put like a solid error bars in there and make sure that things are aligned. It's going to take a bit of time only because we don't want to update it unnecessarily, if you will. And also when I've talked with some of our deep field collaborators and people who are looking into what is expected magnitude we should be looking into and we should be reaching with these observations, and everything is looking well aligned. But hopefully in a few months it will be updated.
Very nice.
But
not that it's bad right now.
No,
for
not that it's bad,
it's really fabulous, really.
The level where we will be satisfied, I think that will take years probably of collecting data, but
Anyone else? Line or?
I don't see any online.
Oh, one here.
I think Mikako Matsuura from Cardiff University. On the medium resolution spectra, I can see out a few features in longer wavelengths, particularly when interesting dust features, that is the critical wavelengths. What is the time scale you plan to improve these artificial features?
The time scale to improve
and what's causing these ones?
I would say, again, a couple of months at least. Yes. I mean, the MRS, as you know well, it's both a very complex mode to take care of, but also it's our most used mirroring mode. So there is a lot of, again, effort going to improve. And I mean, since commissioning and until now, there have been already improvements in wavelength calibration, flux calibration, etc. So that will come. It just, we need a bit more time to settle. But yeah, looking into that.
Thank you.
Okay. So I propose we thank Mark and all the speakers again. We're breaking for coffee. We'll be back at 11.
You just grabbed everything that was new this morning.
Oh, that's perfect.
Yeah. Remember which session you're in?
So it's Wednesday, the morning session.
I think I deleted the old one.
Yeah.
So this was
12 slides. This looks right.
12.
Perfect.
So,
Thank you very much.
It's all right. We just grabbed everything that was new, so hopefully we're all set.
Thank you very much.
Okay.
There
is. I see it there.
So we just grabbed the latest versions this morning. So if you
amazing. Yeah, I did put yes, but I prefer the. I think that's the last slide.
Yeah, sorry. That's the wrong way.
Yeah,
okay. No spoilers, sorry. Save them for later. Hey. Cool. Yeah. Hey. Hey, Natalie. Likewise.
Done here? So they can show you.
Cool. Yeah, likewise. Thank you. Great to see you.
They wanted to see the high. Afternoon. 3. This is you, right? You can be. Anything you wanted to check in particular? No. Oh, we need to. That's not your problem, though. If our battery's about to just.
Tomorrow at the first session, 9:15.
9:15. Tuesday. Thank you for checking. We're about to lose battery on this. Lucky we made it.
Oh, whoa.
Yeah, I don't know if you have a solution to that, but Thomas probably does.
There you go.
Oh, good. Thank you.
Counting power. Well, hopefully.
How do we play? Yes.
That's alarming. Good catch.
Thank you. Everyone has to do it differently.
Cool.
If you can get it up on box and down, wait, this is tomorrow?
Yeah.
Oh, yeah.
If
If you get it to us by the end of the day, at the end of the day, we probably could do another pull down of our slides. I know I'm still missing a few tomorrow, so you won't be the only one. um, yeah, wait, do you have the slides updated? You know what? Are the, you put it in Box. That's the easiest way to pull it down onto here. Just come and I won't remember to do it. So come and at the end of the day, like after the last talk, and we could do it then or during the afternoon break or something. Right now, it's still feeling a little crazed. You can leave it the same name. It just puts a date at the end. That way, so it's fine. It's actually easier because then I know that's the newer one. Yeah. All right, you're welcome. Thank you for coming.
Well, I thought that's why I brought it.
Sorry, I wanted to elaborate because.
Yeah, no, thank you.
Sorry, I didn't see it in person. This is my first time using this. Did you talk? What? No, I talked to him. At the end of the month. Right, good. You want to? They just attract the crowd. Don't ask me why, but and when Ken gave us. Yes. Yeah, three of us are like, check your setting. Hold on, yeah, sorry. But... So if you yes, that's the okay, what's your yes, I will say that right now. Gotcha. But as I mentioned, guys, the audio is live right now. Okay, right now it is. Hey, Thomas, the audio is still live. Yes. Yeah, please. Perfect.
Okay, now everybody can hear us. Everybody, please start to take your seat and quiet down, please. Doesn't run.
Okay.
But you have 20 minutes.
Yeah. After 15?
Yeah.
Okay, yeah.
So you have 5 minutes. All right, I think we'll get ready. Okay. Welcome everybody back to the post-break session. We are here to continue the instruments, hearing about all the instrument performance and also the pipeline in this session. So I would like to introduce our first speaker, Paul Godfrey. I did my best. And take it away, Paul.
Thanks very much. Can you hear me well? Okay. Yeah, so I'll present some results from commissioning on the nearest instrument and also present some features that people should take into account when planning new observations for cycle 2 and beyond. And of course, I'll present this on behalf of the whole nearest team as well as the instrument definition team, Canada. This is the Canadian instrument, science instrument on James Webb. Okay. That's interesting. Okay.
No. Is that okay? Yeah, let's do this. Let's start again. Stop sharing, Thomas.
Doesn't seem to be.
Yeah? Okay. Yeah, okay. Cool. And then there you go.
Okay, the first mode is wide-field slitless spectroscopy, which provides low-resolution spectroscopy over R of 150 over about 0.8 to 2.2 microns over the field of view, 2.2 by 2.2 arc minutes. This consists of direct images as well as dispersed exposure through grisms that have dispersion directions in two different orthogonal directions, which is important to deblend the spectra that, for instance, you can already see here. You take this source with the one right above here, that the two start overlapping in one direction. So that's why we have grism in orthogonal directions to help deblending the spectra. This also, it's important to take this into account when planning observations to choose the right opposition angles. And we have a grism overlap tool on GitHub to help observers test this overlapping of spectra for any given position angle, which is really helpful. This mode is supported both in prime and also in parallel mode, both coordinated parallels with MIRI or NIRCam imaging, or as pure parallel. It's used with 4 different broadband filters and 2 medium band filters to block the specific ranges in wavelength that helps. Otherwise, you would get a lot of contamination in the spectra, compared to, for instance, Hubble, which doesn't use these filters. One thing to really take notice of in this mode is that the PSF for nearest is strongly undersampled below 2 microns. Its Nyquist samples at 4 microns. So this really increases the sensitivity below 2 microns compared to for instance, NearCam, but it does require multiple dithers in order to restore the intrinsic PSF. We have dither patterns available with lots of options, 2 to 16 steps and 3 step sizes that you can choose based on the size of your sources you're interested in. And one thing that is kind of ingenious, if you want, that we have in our dither sets is that when both grisms are used in the 2 different directions, the dithers are implemented such that the overlap in the spatial coverage of the spectra is optimized between the 2 grisms. So you get about 90% of the full field of view in both directions. Yeah, this is the ERO image on this mode, which use the special powers of the galaxy. Galaxy clusters to separate 2 lens images of background galaxies, and this mode was used to confirm that the 2 arcs here are from the same galaxy, background galaxy. Second mode is single object slit spectroscopy, which provide medium resolution spectroscopy of single targets. This is the TSO mode of NIRIS, which is optimized for spectroscopy of transiting exoplanet systems around stars between 7.5 to 15th magnitude. This has extremely high spectrophotometric stability, which is achieved by a cylindrical lens that is mounted on the grism, which defocuses the spectra in the cross dispersion direction. Here is an image which shows these spectra. The spectral trace, this is the first order. The spectral trace is 25 pixels wide and about flat topped, which both mitigates flat field errors and pointing jitter, and it allows observations of the brightest objects among all the JWST TSO modes. There's 2 subarrays you can choose with this mode, which allows different brightness limits, and the target is always placed, within 0.03 pixels from observation to the next, using a target acquisition. One thing you can notice here that the first order and the second order starts to merge at the end of the orders here, and while that can be modeled, it's much easier to isolate the 2 orders by inserting the 277W filter in the filter wheel, which then isolates the end of the first order very cleanly. Now this is a slitless mode, so you're vulnerable to contamination from other objects in the field, and we have an ExoCTK package available on the website through the website, which is hosted on GitHub, which can help again observers choose the right position angles in order to avoid such contamination. The requirement for commissioning on stability of the spectra taken with this mode was that the noise level of the science target stay within 100 parts per million at R over 100 after removing of systematic effects. And this was easily achieved. We achieved about 85 parts per million during commissioning. As you can see here, it's extremely stable. Aperture masking interferometry, which is a unique mode, first interferometry or imaging interferometry in space. This uses a non-redundant mask, which is shown here with non-redundant baselines between all the apertures. The effective resolution given by this mode is about 2.5 times better than for regular imaging. And therefore it allows, detection of companions extremely close to the primary star, with differences in magnitude up to 9 magnitudes. And the smallest separation that can be seen this way is 70 milliarcseconds. Extremely small. And this allows reconstruction, also allows reconstruction of high contrast features in extended sources much better than with regular imaging. Again, this mode is very sensitive to bad pixels, so we're very careful in placing the subarray in an area of the detector where there are no bad pixels in the area, and we use target acquisition again to place the objects, within 0.03 pixels every time. It's normally used with a small subarray to allow very bright targets. It can also be used with a full array for fainter sources. And in addition to the science this allows, it also provides images that are perfect for getting into the holiday spirit. It's normally used with through medium band filters. We also included one wideband filter 270W because it includes an important water vapor band, important for certain sources. It's similar to coronagraphy in the sense that it requires observations of a reference star, to provide the reference PSF, which is optimally chosen with a similar spectral energy distribution as the target, the primary target. And the performance was extremely good during commissioning. We resolved the non-binary AB door after subtracting the reference star. You could easily see the secondary here, which was characterized within 0.5 milliarcsecond in separation and 0.5 degree in position angle. Here you can see the observed detection limits we found during commissioning, which went, in the 480M filter, we went already at 7.5 magnitude contrast with only 10 to the 8 photons, whereas we recommend going all the way up to 10 to the 10th photons. And we expect that it can go to a contrast of 9 magnitudes that way. Then we have regular imaging, with 12 filters in the range between 0.8 and 5 microns. These are the near-cam backup filters, except for one of the medium band filters. This mode is supported in cycle 1 only in parallel mode, parallel to near-cam, or in pure parallel mode. But in cycle 2, we are also going to support it in prime mode. And since it's only one detector instead of 10 for near-cam, one might wonder why would choose nearest over near-cam. Well, one main thing would be that like I said, nearest is strongly undersampled below 2.5 microns. Pixel size is about 4.5 times that of near-cam in that wavelength range. So we're way more sensitive to low surface brightness features. Something to take into account if you're looking at tidal tails or diffuse intercrustal light that you want to characterize. Targets of opportunity would be another science goal where you might want to use this mode for imaging, especially if you don't know the position very well. things like counterparts to gravitational wave sources. Since we don't have a gap in the detector, whereas NIRCam has 5 arcsecond gaps between its detectors in the short wavelength. And another thing would be to add direct images to our wide field slitless programs. If you want to do more filters than you're taking the GRISM spectra for full SED fitting. Again, another example. This just to see the quality of the images. This was supposed to be a sparse field from ground-based imaging, and nothing is sparse. Nothing is sparse for James Webb. It's basically crowded or more crowded. Some features and artifacts that you have to deal with because there's no baffle on the telescope. We have some internal reflections as well around what we call the ghost access point, because they produce ghosts. These are different for each filter, and also not all sources in the field produce ghosts. It's a pretty complicated situation, but we have tools to predict where the ghost will fall for any given source. They're about 2%, up to 2% of the source flux. And again, we have the code available to identify ghosts in the source catalogs. And they can be mitigated very well by using medium or large size dithers, since they move in different directions, different from where the targets move. Here are some examples. This is the ghost access point for this particular filter. You can see that bright stars get, faint ghosts on the other side of the ghost access point. You can see some examples here for one filter. They're kind of weird extended sources, sometimes even double sources. But then on the other hand, some bright sources don't produce ghosts, on the other side of the point. So it also depends on the distribution or where the source falls on the detector. So again, important to use the software we provide to identify the ghosts in the images. Then we have a lightsaber. 2 minutes, thanks. This is light that's coming from the what we call the susceptibility region, which is, over 12 degrees away from the actual field of view. The light can scatter into the detector region via a rogue path, and it produces this, diffuse-ish lightsaber that we call. APT is working on implementing a tool that can, where you can check whether or not there are bright stars in the region that will produce this feature. We have some anomalous PSS spikes that can only be seen in the brightest stars. Also diffuse, more diffuse than the diffraction spikes. This is due to some residue from the polishing of the optics, but it really doesn't impact the science. They're really faint. Also, be careful of bright stars around the field of view. They can cause stray light, depending on how far they are from the detector edges. Can be significant fraction of their source flux, so it's important to, try to avoid bright sources around the detector edges. Can also even be, you can get edge-on galaxy-looking features that are really from stars that are, 13 arcseconds left of the detector in this case. Here, you see several things at the same time here. Here's the lightsaber and also some diffraction spikes from stars further away from the field of view. On-orbit performance, I should probably go over this very quickly since I don't have much time, but the sensitivity is about, or the throughput is about 10 to 25% better, depending on the wavelength, than the pre-launch predictions. This is all adjusted in the cycle 2 ETC, and we have also informed the cycle 1 observers if they were already pushing the limits in terms of how bright you can go. But this is all, for most cases, this is good news, except if you want to go as bright as possible. The PSF quality is extremely good. It's a little bit better than the pre-launch predictions. Yeah, it's as good as we can. Here's the summary. We meet or exceed all the science readiness requirements. PSF quality extremely good, very stable across the detector as well. The strometry is good to about 3 milliseconds across the field. Yeah, that's basically your complete success in terms of commissioning of NIRIS. And I invite you to go, into the documentation for all the features that I mentioned already. Go NIRIS.
Any questions?
State your name.
Claudia Scarlata from University of Minnesota. I was wondering about the blobs, the ghosts that you showed. Do they have always the same orientation, or different stars produce differently oriented blobs? Like a pair of blobs?
The morphology depends on the distance from the ghost axis point. So the further you away, the more extended the ghost looks like. Whether or not they're double blobs, that depends on the filter. So every filter has a different ghost morphology. Yeah, it's not a simple, statement. It depends on a lot of things.
Thanks.
But we describe it all in the documentation.
Other question in the room? I think in the corner, Susan.
And very nice talk, thank you. I'm wondering if you can say anything about how well known the spectral trace from the wide field slitless spectroscopy is known relative to the source. We found, this was a big sort of important issue that we were dealing with, that to sub-pixel precision, it's not quite known yet, and I was wondering if there's any updates on that.
There are not the details about this, but the traces of the various orders relative to the location of the object, I believe are quite well known up to second order. So if you have very bright sources in the field, third order, we don't know yet to sub-pixel or even pixel accuracy. But yeah, so those things are still outstanding. We have to look at cycle 1 calibration data that we haven't looked at yet, where we have more brighter stars in the field to get a better idea of the third and fourth order type traces.
All right, we started a few minutes late, but I think we'll have to move on now. Thank you again so much, Paul.
It's off right now.
And next up, we have Charles Prophet, who will tell us about NIRSpec.
So is this on? Yeah. Okay. Okay. Overall, the near spec performance on orbit is as for most of the other instruments, very, very good. Throughputs in general meet and exceed expectations, sometimes by large amounts, especially for the small apertures, but at some of the long wavelengths, we're actually can be a bit below where we expect it to be. The on-orbit performance for detectors themselves is very similar to pre-launch estimates, but there is some modest increases in the dark current, and as a result, the total noise. Since near spec is, unlike most of the other instruments, the faint object is limited by the detector rather than the sky in many circumstances, that can be important. The MSA is behaving very similar to expectations, although some new shorts have appeared since launch and required a masking of additional shutters. Most of the other mechanisms, as far as the mechanical things do, and the astrometry works very well as protected. The BOTS performance has been very good. I won't really talk much about that, since I'm going to emphasize here the things that, the issues rather than the things that work as well as expected. But I'm sure you'll hear more about that in some of the other talks this conference. And near-spec target acquisition works well and exceeds most expectations. Now, as noted, the dark rates are modestly higher than pre-launch measurements. Tends to be a bit of an enhancer of the detected instruments, probably due to the on-orbit radiation environment. And as a result, the total noise numbers are perhaps somewhat larger than predicted, although these are now much firmer. One of the things to emphasize again, though, is that we have this IRS squared mode, which inserts additional readout pixels compared to a traditional readout mode. And especially for the NOS1 detector, you get a very dramatic improvement in the total read noise, as this tends to eliminate the 1/f noise. For the NOS2 detector, the IRS squared isn't quite as dramatic, but I think the overall characteristics of the data are still somewhat better. So you definitely want to use the IRS squared modes compared to the traditional readout modes if you can. One thing about the detector that wasn't expected and actually affects all the near-IR instruments are these large snowball cosmic rays, which produce these large impacts that can be 5 or 10 pixels wide, appear suddenly, and are rather annoying because they deposit so much charge in one place that it leaks out over the succeeding frames. And there are pipeline improvements going into place to handle these, but they don't quite subtract out as well as cosmic rays, as traditional cosmic rays do, and additional improvements are probably going to be made in the future. Now, the flux calibration is one point where things have been coming along. Getting into the pipelines a bit more slowly than expected. There are 3 different flat fields needed we divide the calibration into 3 different flat fields. One is the pixel-to-pixel response, which was set in ground testing. The S flat is in the internal variation of the spectra, and it's really the part that's calibrated using the internal calibration lamps. And as a result, a lot of the geometry is intended to be in there. While the 4 optics flat is the correction of the part, is the final correction applied, and it's also really the part that's adjusted using external standard stars rather than the internal lamp observations. And so that picks up the flux calibration finally. Now, for most fixed-slit and the BOTS modes, we have finally, as of a couple of weeks ago, delivered the on-orbit FNS flat files, which get good flux calibration, as I'll show on the next slide. One mode, which we're still using these hybrid files, which are based basically on pre-launch data, because the details of how the modes observations were done in commissioning. For the IFU and MOS modes, the hybrid files, I'm afraid, are still in use. Although hoping we're finalizing those, and within the next couple of weeks, we hope to get those in as well. But as we can see, this is an example for the fixed slit modes of standard star spectra. On the left is the current calibration spectrum for this one mode that we were using to find things in flight. We match that one pretty well, as we would hope so. To the right is another observation that was done in a slightly less than optimal way during commissioning of a different kind of standard. And even there, you can see that we're within a couple of percent. And we're going to be examining those. As we finalize the initial calibration, we're going to then be examining those for the other stars that are being observed during the Cycle 1 calibration program. And so we'll hopefully have more to say on that in the next few months. Comparing with the pre-launch throughputs, this is just one example of that in that in this one, basically the squiggly red line is the observed efficiency of converting photons to electrons at the detector. And the solid line was the pre-launch prediction. And this is for relatively wide apertures where the improvement in the PSF that everyone has talked about doesn't matter quite so much. And in that case, we're still, especially at the short wavelengths in the, and especially in the IFU, seeing some significant improvements. At the red end, however, the diffraction losses are somewhat larger than have been modeled in pre-launch modeling. So in that case, we, again, especially for the IFU, sometimes are getting somewhat smaller efficiency than we had estimated. However, for the very small apertures, you can see this is, for example, one of the typical, the S200A1, which is similar in size to the width of the MOSFETs. We get a rather dramatic increase in improvements in short wavelength due to the much better than promised PSF. And as a result of that, we do really significantly increase the throughput at short wavelengths. So we'll get, as a whole, much better performance at short wavelengths. And at longer wavelengths, the performance may be similar or perhaps even not quite as good as the pre-launch promises. Right. Now, there still are some caveats to the absolute flux calibration. Right now, the aperture size you used for the extraction was done using the fixed size. In case the fixed fit, for example, it's a 5-pixel high extraction aperture used. And right now, the pipeline doesn't have any aperture correction available for different sizes of extraction aperture. So if you need to tailor it, it's going to be, a lot of handwork to do the proper corrections for now. And again, that's something we're going to be working on. So far, the files we have are only the one standard star per observing move that was used for creation and the self-validation. And so the uncertainties we're going to, as we finalize the calibration, we're going to have to do some more work on comparing different stars and stars of different spectral types. And so that work isn't yet available. And there's some details in the way especially the geometry. For the near-spec MOS modes, for example, you're actually putting the spectrum on very different parts of the detector, and there's some geometric effects that were intended to be taken into account by the S-flat in terms of especially the how many angstroms per microns per pixel you get at different locations. And the DMS version of the pipeline, unfortunately, isn't handling that quite right. And so that's something else we have to fix and quantify for the systematic uncertainties before you can completely trust your flux calibration going forward. And there will be an extensive Cycle 1, there is an extensive Cycle 1 calibration program going on, which has already collected a lot of data. And so in the next few months, as I said, we'll be working with that. Okay. Now, switching now to the overall geometry of things, NeoSpec depends heavily on its internal model for deciding what goes where. The residuals for the model itself and the grading wheel sensor calibration are very good, within an order of a 20th of a pixel. The residuals for the imaging filters, the filters taking the imaging mode and a geometric solution, internally are within 1/2 to 1.1 to a quarter pixel RMS, which is slightly larger than the ground testing, but that's due to the fact that centroiding the real stars doesn't work quite as well as centroiding the simulated stars. And the grading wheel mechanism, which affects where the spectrum falls in the detector, is very good, and uncertainties from that tend to be below 1/10 of a pixel. Another top issue, of course, is the MOS mode. We have the micro shutter array, which is used for the MOS mode, and has 250,000 individually programmable shutters covering the 3.2 by 3.4 arc-minute field of view. And this allows the multiplexing in MOS mode that allows us to do tens to, dozens of individual targets. During commissioning, we did 800 different reconfigurations to test the shutter operability maps and verified whether shutters were vignetted, which were failed open, which were failed close. And the biggest impact of although comes from the electrical shorts. Now the total usable shutters are about 82.5% of the available 250,000 shutters. 22 are failed open. And for the shutters that work, individual shutters work about 96% of the time. So there is a small chance that in any individual shutter, if you open it, if you command it open, it just will decide that time not to open, which is unfortunate, but it's a relatively low rate. And especially if you're using a 2 or 3 point nods, odds are you'll get it in the other nods, for example. And so it's something that, for the most part, can be worked around, although it does emphasize that you have to be careful if there's one target which you absolutely have to have. It can be a higher risk than for most modes. The other problem is these electrical shorts, which are caused by contamination or defects in the control electronics, can cause some of these lines that control the shutters to be shorted to each other. And this can cause glow in the images. They may appear in different shapes, but almost always result in elevated currents, which can be detected. And unpredictable behavior of the shutters. In some cases, we actually had shutters opening that weren't supposed to open just because they were shorted. And glows that may degrade the science data. For the point of view of the observer, these glows can be the worst problem, since often they're very, very bright and they cast scattered light all over the detector. And if this happens, the odds are that there's nothing the user can do but ask for the repeat, because it's relatively rare that you can extract your science out from under the bright glows, especially the scattered light, although, of course, you have to judge that in individual cases, case-by-case basis. One thing which was kind of unexpected was that sometimes these shorts actually produce glows even when we're using the IFU rather than the MOS mode. Now that was unanticipated because in principle when you're in the IFU mode, all these lines that control the micro shutters, they're supposed to be set to a constant voltage and there shouldn't be any currents floating. But apparently things aren't happening quite as they were. Some shorts do cause the IFU observations to be affected, and that can cause problems for the for those observations as well, unfortunately. And it's also a big impact operationally to have to declare modes not ready and to quickly try to get these shorts masked out on board so that they turn off the lines and glows so that goes away. But we're trying to make that more efficient, but it's probably something that's always going to be happening during your lifetime. Now, for target acquisition, first place, remember that pointing without target acquisition we've seen is good to 10th arcsecond radial. For the IFU and for even some 16 underway observations, you might get away with not actually doing the target acquisition as well. Caveats that you have to be worried about for water, 1.6 by 1.6 arcseconds is the area for water, and it's relatively small compared to most other JWST and HST target acquisition apertures. You have to be really careful about your Doppler motions and your coordinates. And we've had a number of programs, especially for things like faint ground dwarfs, where they've just missed their targets. Also, one thing is the onboard algorithm for doing the target centroiding can actually clip targets if they're faint enough that the bias level drifts downward during the observation. This shouldn't be a problem if you meet the ETC requirements, but if your target's fainter than expected, it might disappear for the TA. So if in doubt about the brightness of your target, go deeper. The MSAT algorithm, which also corrects the roll, remember you also need to register that in roll, and we recommend that you register it to within about 1 arc minute of roll. And if you're larger than about 8.3 arc minutes in the error, it's going to probably fail. And this is just some examples of the results from TAs. After TA, residual error is about much better than spec, maybe 7.5 milliarcseconds. And for MSA TA, we get, this case, the post-reference images show about 25 milliarcseconds, but that's for essentially all successful GO observations. And in practice, it's often, for the best cases, it's better than that. And so I think we're generally meeting the spec we defined in the requirements. But target acquisition is always tricky. The pipeline itself is in the work in progress. As we've noted, that there are some remaining issues with the flux calibration. Not only, the early flux calibration used inconsistent units, which we fix with these hybrid files, but they still have large errors. We have the fixed slit and bot modes mostly in, and we hope to get the rest in the next few weeks. There are still some issues with the calculating. The near spec depends on its model to decide whether to extract the spectrum. And there's still some issues in DMS with calculating that correctly for all the observations. And sometimes it wants to extract in not quite the right place. And so that's another uncertainty in your flux calibration. And there have been some issues. There's still some issues we have to fix with the IFU astronomy. And also so some errors in the cube building, which are getting better, but it's still a work in progress. And you need to work on the, if you have issues, contact the help desk and they may be able to point you to the latest development version of the pipeline, which may resolve some of those issues. Other things will require other workarounds, which they can advise you on, but it's changing, from week to week as the new builds get in. I think I'm about out of time then. Okay. Okay, I'm done. Sorry about that.
Okay, questions?
Great talk. Can you talk a little bit for the flux calibration issues for the IFU and the MOS? Can you talk a little bit about to what extent that's an absolute flux calibration uncertainty that, you think H alpha is some flux, it might be 40% bigger, as opposed to like the relative flux within one spectrum or within two grading settings, about basically how wrong can your line ratio be versus your estimate of the flux of that line?
I think once we get the right reference files in the pipeline and some of these IFU cube building issues completely resolved, then I think the relative flux calibration and most of those issues should go away. Right now, I'm afraid it is highly dependent on, especially with some of these cube building issues, and can produce. I think we've solved most of the issues with these odd oscillations in the spectrum on bad pixels, but I don't think we've solved all of them. And again, over the MOS field of view, comparing spectra at different locations in the MOS field of view is something I think we're only really getting started on testing how well that works. And of course, you have to be careful to use the latest files because some of the earliest files we distributed to the pipeline were really pretty bad in terms of absolute and relative terms. So you definitely need to recalibrate your data. Yes.
So this is Ben Liu from NASA AIMS of Beirut. I have a question about the wavelength dependent systematics. So based on your current estimate, and if we use the latest reference file, what kind of wavelength dependent systematic, especially for PRISM, like from 0.5 to 5 micron region, what level of systematic we should expect for the uncertainty we should place on the uncertainty there?
Right. So you were asking about oops, I exited there instead of going backwards. Let me go back into. I believe you were asking about how the mode-to-mode reliability of the flux calibration.
In one slide, you mentioned that there's little or no wavelength dependent systematic trend across after the absolute flux calibration. I just wonder, what is the percentage level? Do we expect 5%? We should have a pretty good uncertainty relative flux calibration from the shortest to the longest wavelength flux calibration.
Go back to here then. Yeah.
Yeah, this slide.
This next one. There we go.
Yes.
So as you see, again, once we get the right reference files in, I think we've so far demonstrated that those relative errors are probably less than 5%. But we do, again, we do need to do that test for all the modes, and we need to start looking at the cycle 1 calibration data, which has, observing different stars of different types. So, again, right now I'm afraid it's dependent on what status the individual modes flux calibration is in. But I think within the next few weeks, we should hopefully get that down to within a few percent.
And we're going to take one question online.
It's a quick one online. So Noemi asked on Slack if the new efficiencies for the Prism mode are taken into account in the Cycle 2 ETC.
Yes, the ETC will have, the Cycle 2 ETC will have all the updates for the, it has the updates for the PSF, but not all the throughputs the throughputs we haven't delivered to the pipeline yet have not gotten into the ETC yet either, I don't believe. So I think that we'll be updating them. It's available and we'll post advisories.
Need to move on. Thank you, Charles.
Okay. Oh, yeah.
Next up, we have Carl Gordon, who will be telling us a bit more about the pipeline and calibration.
Full screen, please. All right. Hello, everyone. I'm Carl Gordon. I'll talk about pipeline and calibration program. I only have about 40 slides, so I think we'll get to lunch. No, I'll try to go as quick as possible. I know we're running a little late. So I like Jane said, I want to point out this is a team effort across many people. There's no way I can name everyone, but just to point out for the pipeline, it's everything from design, prototyping, coding, testing, documenting, tutorials, etc. It's a lot of work to do a good pipeline. And the same with the calibration. You've already heard a lot about it. It's a huge team effort. So a bit about the pipeline. We definitely learned from the past efforts on this, from standing on the shoulders of previous missions, Hubble, Spitzer, Herschel, etc., ground-based observatories. All the kinds of data we have been taken before, almost completely true. And so we actually took advantage of all that. And we not only learned what to do, but also what not to do. Both things are important. The pipeline philosophy, it's a little different from how things have been developed for pipelines in the past. It was a combined team effort. The algorithms were based on the community best, so we took input from the instrument teams and mode-specific expert teams, and then tried to figure out what the best was, taking advantage of the expertise across the whole JWST project. And where we can, we're using the same code for different instruments, only where possible, right? And this really makes it easier to maintain, takes advantage of the strengths of all the different teams. And really, and another thing that we did was we're providing the pipeline directly to the community. You see the pipeline. There's no closed form you can't see. You can see the development version and all the warts. So, be warned. It is the real thing. Here's kind of a flow of how it happened, right? So we took all this input. It went through one place to do a critical review. We just didn't accept someone's word on what the best algorithm was. We tried to make sure it was the best algorithm. And then it went into implementation for actually, how do we do it? How do we test it? And then as well as how to code it. The user experience, pipelines run automatically on all data. The default parameters are used for all the pipeline steps. The products are produced and archived, raw and intermediate products, all the usual things. And the real key is you can download it yourself and run it and change all the parameters and etc. And especially in this first year, I encourage you to think about doing that because, as you've already heard, the pipeline code is still in development and changing, but also the reference files are changing. And exactly what you get from the archive may be a little dated, even if it only was processed last week, right? We're early in the mission. I want to make a quick point here about the difference between pipeline and data analysis tools. Really, a pipeline is something that automatically runs on all the data and doesn't require a human interaction. And that's an important difference, right? There's lots of things you might want to do to your data, but you know something specific. Oh, I know it's only got point sources, so I can do this 1/f noise removal algorithm. That works great for certain kinds of data. That's a data analysis tool then. That's not really an automatic pipeline, or it's a pipeline you run offline. There's obviously overlaps between these two. So this is kind of how the pipeline's set up. As you can see, there's 3 stages of the pipeline. We do detector effects in the first. We do kind of more flat fields, things like that in the second. And then we do more complex things like combining images from multiple exposures together to make mosaics. And we start with, of course, JWST gives us our input data, and all the data goes into the archive, and it comes from different stages in the pipeline. Notice there's no instrument name on here, and that's on purpose, right? A lot of the instrument stuff all breaks down, doesn't all break down into individual things. Like all the near-infrared detectors are the same across all the instruments. We don't have to actually have separate code and separate algorithms when things are the same. So here's kind of what the first stage looks like. I'm not going to show you all the stages because that's just too exciting for me. So notice things are kind of split here. We have 2 different kinds of detectors, so we split them by detector type. Some of the things are specific just to MIRI, and some of the things are specific just to the near-infrared detectors. And but we also do have common steps that everybody uses. And so this was a way to really reduce our development time, as well as take advantage of the fact that different teams had different expertises. Status, things are working well for a newly launched observatory. And I want to, I'm now old enough that I can remember what it was like on previous Spitzer and Herschel, for example, and we're doing so much better. Of course, there are bugs. There are areas for improvement, etc. And we learn about them both from our own work on, calibration and so on, and from your input. Please do not hesitate to send help desk tickets. Heck, you can even open an issue on the GitHub repository if that's your mode that you prefer. There's lots and lots of data. This has actually been a bit of a challenge. It's in the sense that it's a lot of data, and running it through the pipeline in real time we have to do, and then we have to reprocess. And so how to speed that up, that's one of the things we're working on, is trying to speed up how fast we can run things. But I remind you, this is a lot of data. It's never going to be super fast. One little interesting point is we never designed the pipeline to work on your laptop. That was not a requirement. So the fact it works on your laptop is awesome, but that wasn't our plan, just to be clear. So there are always new features and artifacts, so we put in new steps. For example, you've heard about the cosmic ray-induced snowballs on the near-infrared and showers on the mid-infrared. That is not something we really planned on, but there already is a new algorithm that's slowly being updated and rolled out. Of course, lots of updates to documentation, communication. The reprocessing is happening about twice a month, but not all the data is reprocessed every 2 weeks. Only the data that we think has been affected by the latest updates. Hence, if you think your data might be benefit from it, download the pipeline, download the code from GitHub, and run it on your own data. That's what I do. So there's more information. Obviously, there's algorithm details are on JDocs. Code-focused documentation is on Read the Docs, the usual place. And I'll point out there are 2 papers in prep by myself and Howard Bushouse that will provide some more details. We're working on them as fast as we can. So a bit about the calibration program. What is a calibration program meant? That's one of the things I wanted to point out, right? It's characterization of the instruments, continued characterization from commissioning, right? Sensitivity, saturation limits, dither pattern performance, things like that. That's what I think about when I think of characterization. As well as reference files. Maybe that's the one we usually think about: darks, flats, distortions, linearity corrections, flux calibration, etc. But also optimizing the pipeline parameters. So there's, default values. We have these default values for the pipeline steps. Well, we're going to update them as we get better understanding of the instruments and detectors, and that's part of our calibration program. I do want to make a point here that I think is important to remember for commissioning versus cycle 1. In commissioning, I wrote it down on purpose. We determine if we expect to be able to produce well-calibrated data, and we try our best to get a first shot at it. But that's what commissioning means, and when the mission says go, is because we think we can get good data once we actually get all our calibration data. And cycle 1 is to actually produce that well-calibrated data. Another way of splitting it is, in commissioning, we got our first numbers on how to do flats and so on, and maybe in cycle 1 we'll get uncertainties on those numbers, is another way to think about it. General status, I would say that we're really in the finishing commissioning data analysis, really updating your ground test results. first in-flight results, and this is kind of where near-spec and nearest is, and really all the instruments, but a rough idea is that near-spec and nearest are more in this stage. And starting the analysis of the cycle 1 calibration and starting to announce the updates, refining the commissioning results. I would like to point out we're still taking cycle 1. We're only, halfway through cycle 1, so we don't have all our data yet. And so we're still taking all the observations. And this is more where NIRCam, MIRI, and FGS are, I would say. We're getting started out of commission, to the next steps. A little bit on absolute flux. We've heard a bit about it. One thing to point out is our absolute flux calibration is actually integrated across all instruments. It's a combined program by design. We have a goal to observe 5 stars of 3 different types over the first couple of years, maybe 3 it's going to take us. And the whole idea here is we want 5 stars per type so we can actually quantify the random uncertainties in our flux calibration. And we want 3 different types because we actually wanted to look for the systematic uncertainties. This is kind of an upgrade to what's been done previously. We're trying to push ourselves a bit on the absolute flux calibration. And these are our 3 types: hot stars, A dwarfs, and solar analogs. I'd say right now, and you've already heard about it in the earlier talks, initially our agreement looks to be 2 to 5%, I would say, at a kind of a gut level, watching talks, talking to people, between different calibrators observed in the same instrument mode, right? And that's pretty good out of the box. I'm happy with that. You have to remember our requirements are 5 to 15% depending on the mode, so we're doing great. And I think we're doing the instrument and the cross-instrument analysis is ongoing. That's where we are. Said I'd be quick. Hold on, almost. So if you want to know more about the absolute flux calibration program, we actually have a paper, which is totally awesome. Here's some spectra. If you haven't thought about what spectra of these types look like in the near and mid-infrared, it's nice to look at the spectra. And yes, those emission lines are standard for an LTE model. They're actually normal, but don't mean there's a disk or a wind. And there's different resolutions we have. And we have a whole list of stars. We're going, we haven't observed all these in cycle 1. We're going to continue observing in cycle 2 to build up the sample of different stars so we can actually do the uncertainties. And with that, I'll be done. And with my favorite picture.
Thank you for the speed talk.
Well, it's lunch is coming.
All right. We have time for questions.
So in our papers that we're working on now, what do you recommend in terms of putting in for flux calibration errors?
I think the rough, it depends on the instrument mode, of course. I would say, for imaging, the imaging is, I think, where we know most right now about the flux calibration. 5%-ish maybe, and it gets a little harder depending on other modes. The spectroscopic modes are much harder for me to gauge personally. I'd ask other instrument team experts, but I think it's a little more uncertain there. And
so what you're saying is, if we say 5%, we're being conservative. 5% will be a safe assumption with the analysis.
That's what I would think right now, but there's no reference for you, so I can't be held to it.
I'll quote the talk.
We're going to do a quick question online before going back to the room.
So Sam Federman has asked, are there plans to update the interface for the MAST archive?
Oh, the interface, that is...
Can you answer that, Carl? Carl? Huh? Do you want me to answer that?
Yes, please. Sorry, it's a disembodied voice.
Yeah, sorry. Yeah, there are plans to have a JWST specific MAST interface. It's going to be very similar to what you're seeing as the HST mission specific interface. So it's completely separate from the MAST portal, which will still exist as we transition to that other interface. But that new interface is designed around JWST.
Okay, let's take another question in the room. Your pick, Susan.
Hi, Carl. Cool talk. So, going from absolute flux calibration to pipeline errors, because in our papers we should also report the error, and there's been a lot of discussions what the pipeline gives out and what we empirically kind of gauge from our data. Is there any calibration effort or against characterization effort on this part and the fidelity of the errors that the pipeline puts out?
Yeah, so just a quick summary. The error does put out an uncertainty on each pixel measurement, each mosaic. I'd like to point out it actually outputs the three components of that error that go into the error. So the only errors we're currently tracking in the pipeline are read noise, photon noise, and flat field noise. We potentially could track more. We just don't right now. We're putting them out not as just the total, but also the individual components, because depending on your science case, you probably only want to use a portion of those. I don't think we've done much testing on the accuracy of those errors. I mean, I think we got the photon noise probably right, the read noise right, the flat field noise depends on reference files. The flat's actually coming with uncertainties, the accuracy of our gains and so on. So those are, I don't think I have not seen a bunch of very much characterization to see if those are reasonable. I look forward if people have found that out. I'd love to hear more.
Okay. And in the interest of getting to lunch, let's call it there. Thank you again. And we're back at 1 p.m.
Yes, I believe we're back at 1 p.m. Enjoy your lunch.
1 p.m. Eastern.